Hello everybody, this is Mark. Today I want to give a video instruction on how to create a new simulation using GC-SOS gas chromatography simulation and optimization software. So when you first start the program, you're presented with two options. You can open an existing file or create a new one. Today I want to demonstrate how you create a new simulation file. So you're presented with a data input window. There's a information field containing 6 different tabs. And this is where you enter your information from your actual chromatographic runs. Each field that is in italics is optional and presented there really just as a record-keeping device. So the first tab is method description. I'm going to enter my information and then click Next. The next information tab is the instrument description. Here you enter a brief description of your instrument. And then your carrier gas type, whether you're using helium, nitrogen, or hydrogen, and then the outlet pressure. So for most detectors, you're going to enter in 1 atmosphere. Where you would differ would if you're using something like a mass spec, and then you would basically enter 0. So I'm going to enter 1 and click Next. That brings up the column description. Again, I'm just going to make up some information here. So enter the length, the diameter, the phase thickness, and then click Next. This is the number of data input runs tab. So this is basically the number of training runs that you're going to be using. For this example, I'm just going to use 1 training run. And this could be in many cases, could be your existing separation. So this is where you now enter in the temperature and pressure conditions for your existing run. On the left is the pressure conditions. So I'm just going to enter something in. It requires that you enter in a hold-up time. If you don't know that accurately, you can estimate that using the hold-up time estimation utility. Here we have a estimate of about 53.53 minutes. I'm just going to go ahead and use the estimate. The initial temperature for my particular run was 50 degrees. It was held for 1 minute. It was then ramped at 10 degrees a minute to 120 degrees, where it was held for 2 minutes. It was then ramped at 15 degrees a minute to 250 degrees. Where it was held for 20 minutes. And you can see a graphic representing the temperature profile is provided as you enter this data into the field. So the next information is your analyte information. So this is basically where you enter in information about your peaks, the peaks in your training run. Really, the only information required here is retention time. There are defaults that are used for analyte, name, peak area, and width. If you don't enter that, I am going to enter in all fields. I do have some information in the clipboard. So this is a separation that I've already entered. So I've entered in the name, peak area, width, and retention time for each compound. And so that's all the information that you need to enter for your training runs to prepare a simulation file. Okay, once that's done, a mathematical model of your separation is created and the data is loaded back into the main window. And here you see a graphic representation of the separation, and then the run conditions that were used are captured down below. So here you see a separation. We have a pretty good separation, a minimum resolution of 1.7 and a total runtime of about 38 minutes. I'm going to just do a couple of simulations here to try to improve this separation. I do want to try to maintain a minimum resolution close to what I have in my training run, but I would like to reduce the time a little bit. So basically, you do this using your expert, knowledge of how to improve separation. I.e., you can use the trial and error approach, where you basically, can evaluate a separation very quickly. This is really one of the key advantages of simulation, is that you can, evaluate a separation very quickly without having to actually run the thing, which may take, 20 or 30 minutes or more. Another unique feature of GC-SOS is that we have a novel auto-optimization functionality, and I'm just going to go ahead and use that because I think that is by far the most efficient way to achieve a optimized separation. So like I said earlier, I have in my training run a minimum resolution between all peaks of 1.7. I'm going to go ahead and just see if I can maintain that same resolution and improve the separation in terms of time. So here's my optimized separation. And you can see I did achieve the minimum resolution. This time the run was about 18 minutes. So compared to my first separation, which was roughly 38 minutes, I was able to, using the optimization software, achieve a separation of comparable resolution in about half the time. If your instrument does have a pressure flow capability, you can use the constant velocity. I'm going to go ahead and just do that because that usually is a way to tweak out a few more percentage points of optimality. And you can see we've reduced the time just slightly using the pressure programming option. If you do have a efficient GC oven and you can ramp the ramp rate a little bit higher, you can actually tweak out a couple more percent of efficiency, with that. So here we have 17 minutes. I'm going to, go from 40 to 60 and see what that gives for us. And that basically reduced the time by about a minute. So that just is a good example of how having a efficient GC oven can actually result in a higher efficiency run. So that's basically a quick example. We entered in a chromatographic separation. We created the model. We executed a few manual simulations, and we utilized the auto optimization capability to deliver a improved run that was much more efficient in terms of time, while still delivering a sufficient resolution. Next thing you could do is save the file. A standard type of Windows save option. You could also print the information out to your printer, which serves as a nice record-keeping device. As a general procedure, you probably would want to enter in these optimized conditions into your GC. Go ahead and actually run the run, and you should be pretty close. If you are interested in higher accuracy of simulation, you could actually enter in the second run back into the program if in fact it was run under isobaric conditions. So for example, you could enter these simulation parameters into your instrument, and then if you wanted to, you could take that actual run and enter that back into the program as a second training run for improved accuracy. So this was a quick example. Hopefully you enjoyed something. If you want, you can go to www.gcsos.com for more information, also to download the most recent version of the program. Thank you.